Okay, so now we got negative x1. We need 4 of x2. And we need our input. Okay, so it looks like I got x1 down. So now we need to go into x2. x2 needs negative 2 of x1, or negative x1. So, come around here. That gives me negative 2 of x1. I need 3 of x2. That gives me 3 of x2, and then I need my input as well. And finally, my output's going to be negative x1, I need 2 of x2. And I need 7 of my input, so wherever that input is. Any questions about 3? Okay, so for number 4, we need to find eigenvalues and eigenvectors, okay? So to find eigenvalues, we set the determinant of lambda I minus a to 0. Okay, so lambda I minus a looks something like that. Now I'm going to try to take the determinant. Remember, whenever we're taking the determinant of a 3 by 3, I multiply this by the determinant of the submatrix. And I multiply this by the determinant of the submatrix. Well, that's 0. And I multiply this by the determinant of that submatrix, and that's 0. So really the only one I have to worry about is the first one. So the determinant of this 2 by 2 is lambda minus 3 times lambda minus 1 minus 0. Okay, so the first thing to figure out is that my eigenvalues are 1, 2, and 3. To find eigenvectors, I set A minus lambda I times x equal to 0, and I try to find an x that solves that. Okay, and that'll give me an eigenvector. All right. So for lambda is equal to 1, A minus lambda I. Lambda is 1. So this is going to be 1, 0, 0, 2, 2, 3, 7, 0, 0. Okay. So now, I just go through and solve each of these normally, right? So my first equation gives me x1 is equal to 0. Okay? Knowing that x1 is equal to 0, the second equation says that 2x2 plus 3x3 is equal to 0. And the last equation doesn't say anything. Right? It says 7 times x1 is equal to 0. We already know x1 is equal to 0. So another way to say this is these two are linearly dependent. Okay? So the only thing I've got going for me now is this and that. And all I need to do is find a value for x2 and solve for x3. Okay, so if I make x2 equal to 3, then I know that x3 has to be negative 2. So my first eigenvector is going to be 0, 3, negative 2. My m is equal to 2. That set of equations. So the first equation tells me nothing. It says that 0 is equal to 0. We know that's true. The last one says that 7x1 minus x3 is equal to 0. Second one says 2x1 plus x2 plus 3. Okay, so now I have two equations and three unknowns, which means I can just determine something, right? And just pick anything out of the air, and I know that I can still solve for the other two. All right, so solve for x1 is equal to 0. That's not a good idea. Let's not do that. We'll say that x1 is equal to 7. Or, sorry, 1. So if x1 is equal to 1, x3 is equal to negative 7. No, it's equal to 7. And then I can solve for x2. So 2 times x1, which is 1, plus x2, plus 3 times x3, which is 7, is equal to 0. x2 is equal to negative 23, looks like. So then my second one, I've got 1, negative 23, 7. So the reason I didn't want to set x1 equal to 0, if I set x1 equal to 0, it would have then forced x3 to be 0, which would have then forced x2 to be 0, and 0, 0, 0 is not an eigenvector make, right? That's a null vector. It's nothing. Okay? So they got to be non-zero. Number 3. I've got A minus lambda I so first equation tells me that x1 is equal to 0. It says negative x1 is equal to 0. Second one, 2x1 plus 3x3 is equal to 0. So x1 is equal to 0. If 2x1 plus 3x3 is equal to 0, x3 is equal to 0. And this last equation kind of restates that x3 is equal to 0, right? So I've got x1 is equal to 0, x3 is equal to 0. I have no idea what x2 is. I can choose it at will. That would be my third eigenvector. Okay, and lastly it says, if we label the eigenvectors v1, v2, v3 and create a matrix V, determine what v to the negative 1 times a times v. Remember, that's how we diagonalize a matrix. And since all my eigenvalues are distinct, we don't have any of those crazy diagonalization rules where they have ones on the super diagonal or anything like that. So without doing anything else, I know that my eigenvectors, or eigenvalues, will be on the diagonal. That's what I get. And you do not need to calculate A. Some of you try anyway. Okay, any questions on number 4? Number 5. Okay, so this is the Cayley-Hamilton theorem problem. So I don't know the actual precise way to write this, so I'll just write it the way I know how. So Cayley-Hamilton theorem says if I have a function of a matrix, I can make it equal to a polynomial of a matrix if that function evaluated at its eigenvalues is equal to the polynomial evaluated at its eigenvalues. Then if those eigenvalues repeat, then we have some times where we take the derivative and all that other stuff, right? So the first thing we need to do is find the eigenvalues of this kind. So we'll do our good old lambda I minus A. Set it equal to 0. Something that looks like that. If I take you the determinant, I get something like that. eigenvalues are 2 and -1. So I don't have any repeated eigenvalues, I don't have to worry about any derivatives. All I have to do is find a polynomial.
2 and -1. 2 and -1.
2 and -1. Are we sure? Why don't I believe you? I should look down at my paper. Oh, yeah, that's right. I should learn how to do math. Okay, so what do I write it out, then, there we go. My apologies. All right, so 2 and -1. So my polynomial is going to have 2 unknowns. We're going to solve it by evaluating of each of these things, okay? So h of -1 is equal to -0 minus beta 1, and it's also equal to f of -1, which is going to be e to the -t. All right? It's 1, it's not, no, it's -1, it's positive 2. Okay. So h of 2 is equal to beta 0 plus 2 beta 1. And that's equal to e to the 2t. And so now we've got 2 equations and 2 unknowns we can solve for beta 0 or beta 1. Solve for beta 0, then I've got e to the -t plus beta 1 plus 2 beta 1 equals e to the t. Okay, so I found beta 1. I can solve then for beta 0. Now we've solved for beta 0 and beta 1. Cayley-Hamilton theorem says that my function, e to the at, is equal to that polynomial. Okay? And so it's equal to beta 0, which is 2 plus 2t all over 3 plus beta 1, which is e to the 2t A, which is 1, 2, 1, 0. Okay, you can do that, or you can simplify it. If I add those up, don't make any mistakes. That's what I think I get. Any questions about number 5? All I got for today. So we'll start up here on Thursday, doing new stuff. Yes, sir?
So
You got a
there's no
question?
like structure or something for all those samples.
Extra credit for losing points. You get extra credit for not losing points.
Yeah, it's like, it's like,
Um,
probably,
So,